everyone, I'm Tanvi, and I'm a graduate student at Harvard, and I'm going to be talking about searching for quantum decoherence in IceCube.
Huh? This will be
Okay.
which right?
Yeah.
Yeah. Okay.
Okay. So basically, our current understanding of gravity breaks down at the Planck scale. So the question that we really want to answer is, how does space-time behave at the Planck scale? And in order to answer this, we can think about using neutrinos as interferometers. So just as interferometry has been used to understand the structure of vacuum, such as in the search for ether with the Michelson-Morley experiment, and how gravitational wave interferometry has been used to understand the contraction of space-time, we can similarly think about using neutrino interferometry to measure the small-scale structure of space-time. So why neutrinos in particular? Well, neutrinos can maintain their quantum coherence over very large distances, so they may be absorbed and re-radiated by virtual black holes, which are shown in this diagram. So virtual black holes are microscopic black holes that may be created due to quantum fluctuations of spacetime, otherwise known as the quantum foam. So we study two different interaction modes in this analysis, where first we have state selection, which is shown in these two lines, where a neutrino enters, interacts with the virtual black hole, and then is cast into a definite flavor or mass eigenstate. And then phase perturbation is shown over here, where we have a neutrino that interacts with a virtual black hole to have its phase significantly perturbed by some delta phi. And you can see the effects of these two modes in this figure as well, where we can focus on this solid oscillatory line, which shows the unperturbed oscillation in a long distance. And we can compare that to the average oscillation behavior due to these different interaction modes. So the top two are state selection, where we see it reaches this 50% probability in a long baseline. And this is using a simplified two neutrino assumption for this plot. So that leads to a 1-to-1 flavor ratio in the state selection case in long distances. And in the phase perturbation case, it instead averages out the oscillations in the long baseline. So what we're looking for in this analysis is evidence of the flavor distribution differing from our expectation. So how do we model this? We use the Lindblad master equation shown here, where the first term corresponds to the standard unitary time evolution, and the second term corresponds to the non-unitary contributions from quantum gravity. So we can break down this second term even further, and we call this the decoherence superoperator, where the B's are the Gell-Mann matrices, the rhos the density matrix projection onto the Gell-Mann basis, and these D's we choose to be the simplest matrices that encode the behaviors of the two models that I described previously for state selection and phase perturbation. So we choose these to be diagonal matrices with values of 0 or gamma along the diagonal. And gamma here we take to have a power law energy dependence. And this leaves us with two free parameters in this analysis, which are n and gamma naught. So n represents the energy dependence of our model, and gamma naught represents the inverse of the length at our chosen reference energy E naught. So here we can see what the signature looks like for this model. So these plots show the probability of muon neutrino disappearance in two different decoherence scenarios. So they both have the same value of n, which is the energy dependence. So they both have a quadratic energy dependence, but they have different values of gamma naught, where the one on the left has a larger value. And we see that that corresponds to a larger probability of this muon neutrino disappearance, especially at higher energies. So you've seen this before in a couple of the previous talks, so I won't spend a ton of time here. But for this analysis, we use data from the IceCube Neutrino Observatory, which is the world's largest neutrino telescope. It's located at the South Pole, and it consists of 5,160 digital optical modules, shown over here, which observe Cherenkov radiation in ice. So the figure down here shows a sample event display from IceCube, where each dot corresponds to a single DOM that observes light within the detector, and the size of that sphere shows the amount of light that was seen, and the color represents the time. So here red is earlier, so we see this is a track moving where the muon is moving from left to right. And now that we see how the events look like in IceCube, we can reconstruct them and then use 10.7 years of these atmospheric neutrino events in IceCube for this analysis. So the data that we use is shown on this plot over here, where they're binned into 20 zenith bins, 22 energy bins, and 2 morphology bins for our fit. So we use energies from 500 GeV to 100 TeV, and we use cosine zenith angles from -1 to 0, where -1 corresponds to tracks or to neutrinos that pass all the way through the Earth, and cosine theta of 0 corresponds to horizon events or events that kind of skim the Earth. And then the 2 topologies we use are starting and through going tracks, where starting tracks are events where the interaction vertex occurs within the volume of the detector, and through going is when the interaction vertex is outside the detector. So we fit over 36 nuisance parameters divided into 6 categories for this fit, where we have the cosmic ray spectrum properties, the hadronic production parameters, the astrophysical neutrino flux properties, the neutrino attenuation parameters, which encode the Earth density parameters, and then the overall flux normalization and the detector response, which encodes both the DOM and the ICE modeling. So this figure here shows our results, our sensitivities for this analysis, and it's quite complicated, so I'll break it down. So the top part shows the phase perturbation case, and the bottom part shows the state selection case. And for each of these, we scan over 4 different n values of integer energy dependences from n equals 0, which is on the far right, to n equals 3, which is on the left. And for each of those, we then have the sensitivity of the previous IceCube analysis for the signature, which is shown in the dashed line, the upper limit set by that analysis, which is shown in the dotted line, and finally, the sensitivities of my work shown in the solid lines. And we'll also note that moving to the left on this plot indicates moving to obtaining sensitivity to a smaller value of this decoherence parameter gamma naught. So that indicates setting a stronger constraint. And we see that we obtain the most significant improvement for models with a stronger energy dependence, namely n equals 2 and 3, which are the purple and the magenta lines here. And we can also see the factor of improvement of my sensitivities compared to the sensitivities of the prior analysis. So for n equals 0, we get about a 20% improvement in sensitivity. And as that improvement increases up until n equals 3, where we get about a factor of 8 improvement. But what does this all mean? So we can go back to thinking about the Planck scale. And if we apply a naturalness argument, we would expect that neutrinos of order Planck scale energies would have coherence lengths of the order of the Planck length, just by like a nice assumption. So this plot over here shows the upper limit set by that prior analysis that we were looking at on the previous slide, along with this Planck scale naturalness line, which indicates the point at which we cross and we're sensitive to below the Planck scale, below this Planck scale naturalness. So we see that this analysis would be sensitive to Planck scale physics below the natural expectation for n equals 0 through 2, just as this prior analysis was. So we expect that to be the same with our upper limits as well once we unblind. And n equals 2 in particular is motivated by probing quantum decoherence effects in string theory models. So from a theoretical perspective, n equals 2 is particularly interesting. And then for n equals 3, we see that the prior analysis was slightly above that limit of Planck scale naturalness. And based on the improvements to our sensitivity, we expect that we will still be slightly above that expectation. But we do get quite a bit of improvement for at going even farther below the Planck scale for n equals 0 through 2. So in conclusion, this analysis searches for neutrino decoherence due to quantum gravity using 10.7 years of atmospheric muon neutrino events from IceCube. And we obtain a significant sensitivity boost from the prior IceCube world-leading constraints. And the unblinded results are coming soon, so keep an eye out. Yeah, thank you.
Thank you, Tanvi. Are there questions? Yeah, Ludwig. Thanks for the nice talk. Could you go back to slide 14? And as a
sorry.
I don't understand much about quantum gravity.
Yeah. But
can you explain what n is? I didn't watch that.
Okay, so n here, so n is this energy dependence of this decoherence parameter gamma.
And while we're on that slide, should I understand why it's a 9? why there are 9 gammas and 1 gamma?
So there are 9 gammas because there are 9 of the like Gell-Mann matrix, like it's like a 9-dimensional parameter space.
Okay. Thank you.
As the third and the eighth Gell-Mann matrices is diagonal, whereas the other are kind of parametrizing like in space transition. So that's the reason why we have like these zeros in the there's a place for 2.3. Any other questions? Yeah.
It's just that the measuring is a rollout by T2K and SQL you can see that here. So I think maybe there are other models. In other models, the naturalness is not rollout.
Yeah.
Correct.
Yeah. So this is a very specific model. So and you can see on this plot we have for state selection, we have the T2K limits that were set, and this analysis just probes even farther below the Planck scale.
Yeah.
But it also extends to other values of n that weren't tested in T2K, like n equals 3.
So being a model, what assumptions can affect can increase the limit to close to Planck scale naturalness lines?
Or for you mean for n equals 3?
Yeah.
So this analysis is very sensitive to the astrophysical component, and we're like statistically limited for that regime. So we would require like more events probably to be able to really probe farther down.
Then do you think your model is very toy?
Well, it is like a heuristic model, as a lot of like the quantum gravity like models that are being tested are.
Because I know many so-called quantum gravity model is very you are talking about. Thank you.
I think there was one more question over there.
Yeah, thanks for the talk. I guess what I'm doesn't completely understand is because normally when we like grow neutrino phase changes, we can only do this with relative potentials. So for example, in electron rich matter, we get a difference in phase only because we have electron neutrinos and it's not affecting the other neutrinos. But then I don't understand, since this, I can imagine these micro black holes would affect those states in a similar.
Yeah.
So how do you differ between maybe just a mass correction and an actual oscillation phase correction?
Yeah, so this analysis is looking specifically at muon neutrinos. So we're looking at tracks within IceCube, and electron neutrinos wouldn't, and like tau neutrinos wouldn't produce tracks within the detector for the most part. So that's how we're like only looking at one of the flavors in this analysis, if that makes sense. If that answers your question, I'm not sure.
We can talk about it.
Yeah.
Okay, let's thank Tanvi again.